Okay, we're going to talk about Newton's first law of motion today. Um, because this note is rather heavy on the text, I am doing one of these talk-throughs. So this is just going to be me. Um, I've opened a PDF on my iPad. I'm just going to kind of talk you through what's typed here. I'll add some audio to what you're working through. Hopefully that helps. This first blurb here, the background blurb, um, since you're doing this at home, um, you're going to kind of have to think things through. Like I ask you questions, and literally, I want you to imagine what the answer is. I'm going to ask you like about car crashes. I don't want you to go out and get in a car crash, but just imagine what would it feel like in your car for these different scenarios. So you are going to have to do some thinking. I am going to talk you through it in this little video clip, but I'll pause and have you think before I kind of tell you the answer. Here is Newton's first law of motion. Objects at rest tend to stay at rest. Objects in motion tend to stay in motion, unless the objects are acted on by an unbalanced and external force. Before we go much farther, it's labeled as Newton's first law. Newton was kind of a weird, cranky academic, so he was very rigid and academic in how he wrote things. He didn't create Newton's first law of motion. He just calls it Newton's first law of motion because Newton's second law of motion builds off of this, and then Newton's third law of motion builds off the first two. This particular law of physics was originally thought of by a guy named Galileo. Um, Newton just incorporated it in his larger body of work. Galileo, he's the guy that kind of, I don't know if he came up with it, but he used the word inertia. In chemistry, we say chemicals are inert. It means they don't react. In physics, when we say things are inert, we mean they don't react in terms of their motion. If something's at rest, it just doesn't magically start to rest. It's inert. It's going to stay at rest. If something's moving in a straight line, it doesn't speed up or slow down unless something makes it speed up or slow down. Or if something's moving in a straight line, it won't turn unless something makes it turn. That's what Newton's first law of motion is. To really get it though, we're going to spend a bit of time. You're either reading about it or listening to me talk about it. There's two parts to Newton's first law of motion I want to go over, the unbalanced and the external. So in order, we'll tackle the unbalanced part first. Bottom line is forces are vectors. We have to take into account the direction when we think about forces acting on something. So here's this imagination part. Imagine you're in a crowd of people. Imagine you're in a crowd of people and you get pushed a little bit. As you're standing there, two people bump into you. One person pushes you to the left and the other pushes you to the right. So you're standing in a crowd of people, someone accidentally pushes you to the left, someone accidentally pushes you to the right. You're going to be able to think this through and know the answers. But what if the force to the left is larger? What would happen to you? What if the force to the right is larger? What would happen to you? Or what if the kind of Goldilocks thing, what if the forces are just right? What if they're the exact same size? Basically, what Newton's first law says is that if the forces are balanced, then your motion won't change. So in this situation, if one force overpowers the other, then there's going to be a change in the motion. So back to the question, if the force to the left is larger, then your motion is going to change. You're going to move to the left. If the force to the right is larger, then your motion is going to change. You're going to move to the right. But if the forces are exactly the same, then we say they're balanced, then you're not going to move left or right. So since forces are vectors, we have to take into account their direction. If those forces cancel each other out, then according to Newton's first law, they're not going to affect your motion. You're going to continue being still. If you were moving, you're going to continue moving in your straight line. So it takes an unbalance in the forces. One has to be bigger than the other to make you move. Okay, the second part, and if you peek ahead, you can see it's the classic Wile E. Coyote from that Roadrunner cartoon. It used to be around when I was a kid. I don't know if you guys have seen it. Objects, Newton's first law thing says objects in motion stay in motion, objects at rest stay at rest, unless there's unbalanced, we talked about that, or external forces acting on the object. So my little imagination for this one is imagine you're sitting in your car and you shove on the dashboard. versus imagine you're standing outside the car, standing on the ground, and shove on the car. Maybe even reach in the window and shove on the dashboard. So someone sitting in the car shoves on the dashboard versus someone standing outside on the ground and they reach through the window and they shove on the car, on the dashboard. The external part says for you to change the motion of an object, you have to be connected to kind of a third thing. If you're in the car and pushing on the car, you're internal to the car, you can't really change the motion of the car. But if you're outside the car, then you're bringing in another object. If you're outside the car, standing on the ground, pushing on the car, you're external to the car, then you can change the motion of the car. If you're sitting in the car and push on the dashboard, since you're internal to the car, you're not going to change the motion of the car. Newton's third law comes into play to explain this part really well, but hopefully kind of intuitively, for you to change the motion of something, you kind of have to be external, is the physics word. You have to kind of be outside of it. If you're standing on the ground, then you can push a car. All right, a little bit more on this note. I call this Newton's first law in the real world. There's a cool connection between forces and acceleration. Inertia is the word I'm going to use, and what you feel. So first scenario, let's say you're in a car and it's at a red light and the car turns green and you hop on the gas and accelerate forward really quickly. What would that feel like in the car? Well, Newton's first law says objects at rest tend to stay at rest. You've got inertia. If you're not moving, you want to stay not moving. If the car accelerates forward, you kind of want to stay still. So it feels like you're pushed back in the car. That's what it feels like. But really what happened is you stayed stationary for a split second as the car accelerated forward underneath you. So when a car accelerates forward, it feels like you're pushed back. You're not pushed back. There's no force of the universe that pushes you backward in the car. It's just you tend to stay still as the car jumps and accelerates forward kind of underneath you. So you feel like you're thrown back, but really it was just the car accelerating forward underneath you. I'm not going to show the YouTube clip, but you can watch it. When cars accelerate forward really quickly, the issue is you could get whiplash. Your seat is designed with a headrest to make sure that doesn't happen to you. Okay, next thing to imagine, what if you are driving down the road and the car comes to a sudden stop? What would that feel like? So use your imagination. You're in a car slows down quickly. What does it feel like? What is actually happening? It comes back to inertia again. You're in the car, you're in motion. When the car slows down, inertia is a tendency to stay in motion. So you're in motion, you tend to stay in motion. You keep moving forward as the car slows down around you. So it feels like you're pushed forward, but really what it was is the car kind of slowed down and moved backward in a way. Relative motion, it's like the car moved backward as you kept going forward. In a modern car, we put in some seat belts and airbags to make sure you don't crash into things in front of you and hurt yourself. It feels like you're thrown forward, but really it's the car accelerating backwards underneath you. So these two, in the first one, when a car accelerates forward really quickly, it feels like you're pushed back in the seat as the car accelerates forward. In the second one, if the car decelerates, which really is accelerating backwards, when it accelerates backwards, it feels like you're pushed forward. Okay, if that made sense, let's try scenario 3. If you're riding in a car and the car takes a sharp turn, I typed it saying the car turns to the right. So imagine you're in your car turns to the right. What does it feel like in the car? Based off of what it feels like and what we've said about inertia and what it feels like versus what's actually happening, what's actually happening? All right, more inertia as the car turns to the right. So I'm going to try and do an aerial. Let's say we've got a car. Here's the road, let's say. Here's the top view. So there's the roof of your car. Maybe you're driving. So pretend it's a convertible. We can see your head as you go around the corner. Because the car is connected to the road, sticky tires, external forces, your car is going to turn and eventually end up over here. It didn't continue on a straight line. It turned to the right. Your inertia, though, inertia says you want to keep going in a straight line at a constant speed. So your head kind of wanted to go, your whole body kind of wanted to keep going that way, but the car kind of moved to the right underneath you. So when a car turns, it feels like you're pushed to the outside, but really what's happening is that's just your inertia wanting you to go in a straight line as the car turns underneath you. The bottom line of inertia is, the bottom line of Newton's first law is this first part, is things are only going to accelerate if there's an unbalanced force. The motion is only going to change if there's an unbalanced force. If two forces act on you and they cancel out, your motion's not going to change. If one of the forces is bigger than the other, then your motion will change. The force has to be external. And then this cool little bottom part here, our bodies have kind of got built-in accelerometers. We can feel acceleration, we just feel it backwards. If it feels like we're pushed backwards, really what happened is the car or whatever we're in was actually accelerating forward. If we feel like we're pushed forward, really what happened is the car or whatever we're in accelerated backward. If it feels like we're pushed to the left, really what happened is the car or whatever we're in turned to the right. That's all the talking I really want to do about this one. There's a couple YouTube links in there you can watch. There's a check-in problem related to that. These links here are kind of dead because this is just a PDF I scanned in to make the video clip about. One last thing I'd like you to think about is imagine you're in an elevator. If you're in well, actually, I don't want to give it away because I think this is the hand-in or the check-in problem. But what would it feel like in an elevator as an elevator accelerates one way versus the other way? Think back to what we said about the accelerating car. See if you can transition that and apply that to what you might feel in an elevator as an elevator accelerates one way or another. That check-in problem 2-1, I've changed it from quadmaster to quadmaster. So sometimes it's based on an elevator, sometimes it's based on a car. But hopefully this clicked. What does it feel like if an elevator accelerates one way or another? That's my blurb for this note. As always, if anything's bugging you, shoot me an email and I can talk you through it.